Okay, so things going. So I guess we'll get started. All right, chapter 4. Chapter 4 is on forces. So there's Newton's 3 laws. The first law basically says something that's in motion will remain in motion unless it's acted on by another force. So stays in motion unless another force. So I'm sure everyone's heard this, but this is probably really counterintuitive because for the most part, like if you throw a paper airplane, it kind of flies backwards. You throw a baseball and it hits the ground and it stops. We're used to things stopping. The reason things stop is because there's all these unseen forces. Like wind is a force, friction is a force. So we don't really live in an environment where there are no forces. But if you were in space and you threw a baseball, it would just keep moving forever and ever and ever and ever and ever. And that's all that Newton's first law is saying. So the second law is basically a summary of the formula. So for chapter 4, there's essentially one formula that applies to pretty much everything. There's a lot of analytical stuff, but for the most part, the sum of the forces is equal to F net is equal to MA. And let's just do an example right now to explain exactly what I'm talking about. So if we had a box and somebody pushes on it with 100 newtons to the left. I'm a little ahead of myself. Newton is the unit for force, and forces are merely the acceleration of a mass. So any mass that is accelerating has a force. So we're pushing on this essentially with 100 newtons to the left, and then we have a 50 Newton force to the right, and a 30 Newton force to the right. And we basically want to know how fast is this 10 kilogram box accelerating. Well, the way that we apply this formula, the way I recommend, is you can say whatever direction you want is positive. I recommend the numbers will be easiest if you kind of guess which way the direction is going. In this case, it looks like we have 80 to the right and 100 to the left. So we're going to guess this box is probably going to move to the left. So in that case, we say the left direction is positive. We don't have to, but it will make life easier. So we're going to conclude then that left for this particular problem is positive. So it's 100 plus, so the sum of all the forces. This is vector addition, left and right. So 100 plus negative 50 plus negative 30. That is the left-hand side of this equation. That was the sum of all the forces. The 100 vector, the 50 vector, and the 30 vector, the sum of the forces. That's equal to the force net, which is also equal to the mass times the acceleration. So all of this is equal to the mass, 10, times the acceleration. And this is 100 minus 80 is going to give us 20, which is equal to 10A, and 2 is equal to A. Obviously, that's way easier than any question you have, but that is exactly how you should approach every single problem. The sum of the forces is equal to MA. So a lot of people just say F equals MA. That is confusing. I would highly recommend not just thinking F equals MA, F net equals MA. Yeah?
What would the units for A in this case be?
This would be meters per second squared.
Oh, even though it's a kilogram? Or...
Even though it's a kilogram, yeah. So you certainly could have a gram per mile second squared, or gram per mile squared. But that's usually not the point of the exam. So you might have one question where you have to do like conversion factor, right? They give you miles, you have to go to meters, they give you hours, you have to go to seconds. But for the most part, they're gonna be nice, and you can just assume it's, it's meters per second squared. In the concept of Newton, it automatically implies kilogram. So a lot of people would assume, well, it's seconds, it's meters, it must be gram, but the preferred unit for mass is kilogram, not gram. So I would say if they do give you gram, convert to kilogram, because grams is not the same thing as newtons. So all of this was just a summary of Newton's second law. I also just want to make sure the camera's on, because I'm really paranoid. And we're good. Okay, cool. So this is just the second law, so I'm going to erase all this. Oh, wait. Does everyone have it? I'm going to send you the video also, so you guys will have the video. You know how much an hour video memory is? It's like 10 gigabytes of data. So I had to delete an insane amount of like vacation photos just to be able to even like do this. That saved it, but it was someone on like a library computer is going to be going through like the recently like uploaded, be like, this is weird. This is like a lot of like pictures this guy eating. Gelato. Okay, third law. So first law, something stays in motion unless acted on by another force. Second one is just the formula. And the third one is really saying for every force has an equal and opposite force. So every force is an equal and opposite force. And this is something you all probably heard at some point. I wouldn't really think about this so much. This won't, don't look for this to be the case in every single problem. It is always true, but it's not always helpful. So basically this is saying, if I punch the board with like 100 newtons of force, my hand hurts. And the reason my hand hurts is because when I punch it with 100 newtons of force, it punches back with 100 newtons of force. This is best summed up with another like Venn diagram, or not Venn diagram, free body diagram. So if I have a box that weighs 10 kilograms, so we'll also bring into another concept. Everything that's on Earth, and you can almost always assume it's on Earth, has a force gravity associated with it. Force gravity is the most reliable force of all the forces. Gravity is never going to let you down in any of these chapters. It's always going straight towards the center of the Earth. So that's not always straight to the ground. Like if it's on a slope, it's still going towards the center of the Earth. So it's going down here, center of the Earth is down here, and it's always equal to the mass times the gravity. So that's 10 times 9.8 is 98 newtons. We need something to counteract that. There's an equal and opposite force, and that's the Earth. The Earth is pushing back up the ground with what we call a normal force, also equal to 98 newtons. Force normal is a really, it's a fickle variable. So force normal really stands for any sort of retaliatory force. There's a lot of different times we'll say force normal, and it's not always the ground pushing up. It could be tension in a string. It could be like a box pushing on another box. There's a lot of different instances where force normal would be applied, but it usually has to do with Newton's third law, is that it's a retaliatory force. Yes?
So if you punched the board and it broke,
Mm-hmm.
do we need to worry about that? Because that wouldn't be like equal and opposite.
So sometimes it's hard even for me to think about exactly how is this equal and opposite, but the idea is that it will always be equal and opposite, even if we are not, even if you're not showing it. So I'm trying to even think, how would I explain that example where you're punching through the wall?
Well, is that like the same thing when you're pushing on something and it's moving? Because like the thing, like the table is pushing back with the same amount of force, but it's moving because there are multiple forces acting on that object.
That's right. So you can push something and still have Newton's third law occurring, and it's still moving.
Right. What about like the break?
So one of the things about, so that's why I'm saying don't worry so much about it being represented in your diagram, because what your diagram is always representing, and this is the very next, so we're going to erase this and then I'll kind of address your question.
Okay.
So Newton's third laws, that just kind of background knowledge. He might ask, like, this is an example of what law? I wouldn't say it's really high yield, but they're referred to, and you should just know what they are. Okay, so what a free body diagram looks like. So yeah, if I'm pushing this, so this is force push from me, and it's equal to 100 newtons. The free body diagram only shows the forces on the thing that's being pushed. So I'm not showing any of the retaliatory, like, reverse force, just because it's not relevant. But even if I'm pushing it and it's accelerating, the idea is it's still pushing back on me. If I have a chair, I can push a little bit of force on it and I can accelerate it. and it still pushes a force back on me, but we wouldn't represent that in our diagram because the diagram is only concerned with the thing that's being acted upon. So I could have a completely separate free body diagram for me pushing it with the retaliatory force, normal, but that will very rarely be helpful. And that's why I kind of say, here's the third law, but don't really read into it too much. It mainly applies for the ground pushing back on you, or tensions in a string being equal, and it'll come up in like problems. So rather than expect the third law to always, show up in your problem, it's probably better if you just do the problem and realize instances. Oh, these are equal because of Newton's third law. And so it should be like a pleasant surprise when it does show up. You should never look for it. It won't help. Okay, so that's kind of the intro. We're going to write the main formula that you need up on the board. So that is the sum of the forces. This just means vector addition is equal to force net, which is equal to MA. And, this is just transitive property. We don't really need force net in there. We can kind of resum this up as the sum of the forces is equal to M times A. This is our formula. That'll get us through pretty much everything. And again, more analytical stuff, but we'll get to that. So first type of problem is when you have a bunch of things like pushed together. Because this is really common that you don't just have one box, one thing being acted upon. So let's imagine we have a 10 kilogram box next to a 20 kilogram box next to a 30 kilogram box. And we're pushing into it with 100 newtons. Now, you guys are only doing chapter 4. So for the most part in chapter 4, you don't normally assume friction is there. So first step, when you've got a bunch of things together, I'll wait a minute if I were to write it. So okay, first step, push all the boxes together. Just think of it as one big box. So you consolidate all of the masses into one big mass. You solve typically for the acceleration, maybe for something else. And then you come back to your original drawing and you finish solving it with all the individual masses separate. So okay, 10, 20, 30, this is just basically a big 60 kilogram box. 60 kilograms. And I'm pushing on it with 100 newtons. So this is the first free body diagram we're really doing. So let's think of all the forces that could be acted on here. There's a forced gravity. There's always a forced gravity. And the forced gravity is just equal to 60 times 9.8, which I want to say is 584, but I don't know. So I'm going to look that up. 60 times 9.8, 588, good. So this is 588 going down. If it was only, if these were the only two forces, that means, so you have to keep the x's and the y's separate. So this is very similar to chapters 2 and 3. We have x movement and we have y movement. If you only had a forced gravity, what we're implying is that this is accelerating towards the center of the earth. But it's not, and we know it's on ground. The ground needs to push up and oppose this gravitational force with the equal amount, 588 newtons. So if I just looked at the sum of the forces equals ma for the y direction, I would get, so which direction do we want to say is positive? Oh, we could just pick one. So we're anticipating it doesn't move in any direction, but let's just pretend up is positive. So we'll say 588 minus 588. So this is minus, obviously, because it's going the other direction. This will be equal to the mass, 60, times the acceleration. And we'll get that the acceleration is 0. But that's 0 in the y direction. So this is something that should become so obvious that you guys don't even have to write it down. It should just be, oh, obviously the downward force and the upward force cancel. It's not moving anywhere. Also, intuitively, a box isn't just going to accelerate up into the sky or accelerate down to the earth. The reason for that is the gravitational force going down is equal and opposite, Newton's third law, of the upward force normal. So the acceleration is 0. That didn't really tell us anything, but it's just an example that you need to separate the y's with the x's. So there is no friction. So there is nothing pushing on this box to the left. Remember that this box is just all of these boxes kind of combined together. So in this case, the sum of all the forces, well, there is just one force. 100 is equal to 60 times A. And 100 over 60, I should not need a calculator for that, is 1.67 is equal to the acceleration. That was the only thing that we needed from it. So basically we had a 10, a 20, and a 30. The first step is you say, smush them together. That's just a big 60 kilogram. 100 newtons pushes a 60 kilogram. Sum of the forces equals MA. Our A is 1.67. So I can erase all this. I didn't need any of this. I only needed it to get the acceleration, which I now have. So now I'm going to approach, let's say that the question is, we want to know what force does the 20 kilogram box push on the 10 kilogram box? There's a bunch of ways they could ask this. They could just say draw the free body diagram for all of these boxes. Or let's say that they're specifically asking for the force that the 20 applies on the 10. And you could be thinking, how do we even know that the 20 kilogram box applies a force on the 10 kilogram box? Well, let's draw what the free body diagram for this box could look like. Okay, so this is our 10 kilogram box. Notice we keep the 100 newtons. The 100 newtons is not ever changed. The 100 newtons is applied directly to the 10 kilogram box. So it's 100 pushing the 10 to the right. And our force gravity is not changing. The force gravity is very consistent. It's just the mass 10 times gravity, 9.8. So it's 98 newtons down. And it's very similar to what we just did and what we're going to do in pretty much every problem. The force normal then goes up also with 98 newtons. And so it doesn't go up or down because the sum of these forces is 0, which makes the acceleration 0 in the y direction. So that's just something intuitively that we would always expect that we can now mathematically explain. So let's assume that the 100 Newton was the only force in the 10 kilogram box. Let's see what the acceleration would be. It would be 100 is equal to 10 times A. We would get A is equal to 10. This does not match the acceleration we found earlier. They have to match. The acceleration we found applies, everything is moving together at 1.67 to the right. When things are connected, they move as a system, which means they all accelerate together and they travel at the same velocity. So we found it was 1.67, so we know that this is a garbage number. The only way to make sense of that is something must be pushing back into this. And this is the force of, if we call this box A, and this box C, B, and this box C, we can say that this is force like B on A. In other words, the retaliatory force that B pushes onto A. And we just know that that has to exist because we just checked and we saw the accelerations don't match up if we don't assume that this is here. So I can rewrite the sum of the forces. What direction are we assuming everything goes, right or left? Right, obviously it's probably gonna go to the right if it moves at all. So we're gonna say this is positive, 100 minus force B on A is equal to the mass 10 times the acceleration, 10 times A. But we know A now, we know A is 1.67. So I can just write that in, 1.67. And that's 100 minus 16.7 is 83.3 newtons is equal to force B on A. So this is 83.3. That's the free body diagram. So that would be basically at the end of this question. So I pushed into the 10 kilogram box and I'm going to move everything to the right at 1.67. But I mean, imagine this was your like face. Imagine somebody's pushing your face into a 20 kilogram block. Your face is going to get kind of smushed and hurt. That's because someone's pushing you into it. The block is technically pushing right back on you. That would be what would hurt your face, is the retaliatory force of B on A. And we just solved for that. We said it's 83.3. To really just hammer this in, let's see what the free body diagram would look like for this. So we know the 100 is applied to the 10, and then it's applied 83.3 to the left because of block B, which gives us an overall acceleration of 1.67 for the 10 kilogram to the right. First, before we do the second one, questions on the first block, what we were doing? No, okay. You guys can ask questions just because there's, okay, so 20 kilogram, all right. So this is big, and this throws some people off. We are not going to say that there's 100 newtons acting on the 20 kilogram block. The 100 newtons is specifically and directly applied to the 10. What pushes block B, so forces have to be direct. The 100 newtons is directly contacting the first block. It is not contacting directly the second block. So the thing that pushes block B directly is block A. So this will be force A on B. And let's assume we don't know what this is. Actually, no, I take that back. We do know what this is. What was the force of B on A? 83.3. 83.3. So what can we guess that the force of A on B is? 83.3. This is another example of Newton's law where you kind of just have to say, oh, they're the same. It'll just make the problem way easier if we get used to assuming things like that. So another example that we'll see later is if like there's a rope and I pull you with the rope, we could say it's a tensional force, I pull you with 100 newtons. That means like I'm pulling you back with 100 newtons essentially. So usually the tension in both sides of the rope is the same, as is the force in a case like this. So the force of A on B here, we just said is 83.3. We have a downward force gravity of 20 times 9.8, it's 196 newtons. A normal force, we're just going to get used to assuming it, is 196 newtons. There will be cases where they're not equal and opposite, but they're very rare and you really have to think about it. Most of these questions, it's going to be clear that they're just talking about the x direction. Okay, so it's more chapter 5 where you start relating x and y direction for forces. So again, we can, we're going to assume that there's a force of C on B. But even if we didn't assume that, we could prove that mathematically. If I assume that there was no other force, like I'm done with my free body diagram for block B, I could say, okay, cool, let's use our super awesome master formula which solves everything. Let's say 83.3 is the only force going in the x direction. 83.3. We, of course, don't include these because these are y forces. And we don't want to muddle the x with the y's. So 83.3 is the sum of the forces, which is equal to the mass, 20 times the acceleration. 83.3 divided by 20. Acceleration is 4.165. That's garbage. That's not the number because that doesn't match this. So that's just another way of saying, oh, okay, I must need another force coming here. And this we can reasonably call the force of C on B. C on B. So we're going to redo this. So this gave us a bad answer because we didn't have the right free body diagram. We didn't think about this other force that was acting on it. So I'm going to say 83.3. I'm just kind of assuming it's going to go to the right, which it is. So I'm going to say this is positive, which makes force C, we'll call it force C dash B. C dash B, C on B, equal to the mass, 20, times the acceleration. The acceleration, though, we know is 1.67. That's the whole reason that in the very beginning, we put all of the blocks together. So this is 1.67. And now we have one variable. Look at that. 20 times 1.67, 83.3 minus that number, 49.9 is force C on B. Cool. You know what? I wasn't going to, but let's just finish it. Let's just bring it home. Let's do the free body diagram for the third block, block C. So block C is 30 kilograms. Again, we cannot say the 100 newtons is applying on it because 100 newtons is only applied directly to this one. It's kind of distributed weirdly through the blocks. So this is force B on C. What are we going to conclude force B dash C is? 49.9. It's Newton's third law. It's equal opposite of C on B. So this is 49.9 to the right. Down 30 times 9.8 is 294. Force gravity is 294. You know, at some point you don't even have to write the force gravity, force normal, because you're going to realize they're not part of the problem. But for now, I guess it's a good habit. And it will be important later, because later in chapter 5, and they might allude to it now, it's the only reason I'm mentioning it, the force normal is directly related to the frictional force. The bigger the force normal, the bigger the frictional force. But I don't think you guys really have done much with the frictional force, so we're not really including friction. So force normal is going to counteract the 294. Otherwise, it would accelerate to the center of the Earth, which does not happen. And it can't be greater because that means it floats into the sky. Also doesn't happen. So in this case, there's nothing to push back on the 30 kilogram box. I'm going to assume that there is no retaliatory force going to the left. And there's no friction because it's chapter 4. So let's say 49.9. That's the sum of our forces. That is equal to the mass times the acceleration. The mass, 30, times the acceleration, 49.9 divided by 30, and 1.67 is the acceleration. And finally, it does match. That's just a way of proving that we did everything right. If they didn't match, that would have been really bad. And we would have wasted a lot of time, but they completely matched. That's how you would have found the free body diagram for this thing as a combined unit, the free body diagram for just this, the free body diagram for just that, or the free body diagram for just that. Noticing that there was a Newton's third law thing going on in between A and B and C, and that the 100 only applies directly to the first thing. It's kind of channeled weirdly through, but you would never say 100 newtons applies to that or it applies to that. So that's a bunch of boxes together. Let's do a similar one, but now with ropes. Questions on that though, before we do go to the rope
There's
one?
no such thing as A on C or C on A, right?
That's right, because that's right. So our way of thinking about forces, it has to be directly applied. It'll indirectly be channeled, but not directly.
Okay.
All right, so now this is almost the exact same thing, but it'll just look kind of different. And they don't have to draw the things to scale. So this is 10 and this can be 20, and you know, it just won't look twice as big. Maybe it's denser. So force pull is equal to 80 newtons. Actually, I want to make this one harder. We're going to make this harder. This is 20 kilograms, but we don't know the mass of the left block. Okay, this problem seems different. It's the exact same. We don't need a new formula. We're going to apply all the same methods. So, boom, this is a system. When things are in contact, whether they're directly in contact or through a rope, make it a big thing. So this is really just 20 plus m. That's the mass of the big thing. We're still pulling on it. That hasn't changed. With 80 newtons. Okay, so I have a force gravity of 20 plus m times 9.8, but I don't really care because I'm going to conclude that is going to be counteracted by my force normal, which is a safe assumption. So I'm not even going to worry about the y's because I know, one y minus the other y is equal to 0. So there's no acceleration up or down. So I'm only concerned with the x direction. And in this case, there's just the sum of the forces in the x direction is just 80, is equal to m, 20 plus m times a. But here's the last bit of information you'll need. They're going to say that I guess you would need, I'm trying to think about how to do this. Let's say in this case they were going to ask for a forced friction. So friction will always oppose movement. So this isn't going to be like as in-depth as the chapter 5 friction problems, but if we're pulling it to the right, that means friction is going to pull it to the left. So our force pull is to the right. They're saying, okay, in this problem you can assume there's friction. So force friction to the left. But they're going to tell you that you're pulling with 80 newtons to the right, and the whole thing moves at a constant velocity. Constant velocity is like the biggest trick that you'll see. Not even a trick, you should get very used to it for like a lot of the later physics chapters, starting here. So constant velocity, if we have a constant velocity, what's our acceleration? 0. So if our acceleration is 0, that means the sum of the forces is 0. That's a forever thing now. So they're going to say that the acceleration is 0 if it's a constant velocity. In which case we can say 80, we can basically say force friction. Let's say that the left direction is positive. That means the right direction would be negative. Force friction minus 80 equals 0. Force friction is also equal to 80. It would have to counteract it. Yeah. We're not actually going to solve for m, because I realized as I was doing this, I would have to give you guys more details about force friction to solve for m, which we're not supposed to have. So I think it's enough for this problem just to get the point across that if it's moving at a constant velocity, you're going to say the sum of the forces is equal to 0. The problem wouldn't have changed one bit if we said the constant velocity was to the left. It also wouldn't have changed if we said it was completely stationary. And that seems weird, but in all of those cases you have a acceleration equal to 0, and therefore force net equals 0. So the main takeaway of this, forgetting about the m, because that was me doing an anachronistic chapter 5 thing, is just that the force friction here would have to counteract the force pull to the right. I'm trying to think what was the next problem I had in my head. An elevator problem. So if we have an elevator, it's got a cord that pulls it up, like a cable. Cable pulls it up. Often if there's a cable, sometimes they'll call it force normal, but a lot of times they'll call it tension. So you'll see it as T, or F sub T, or F sub N, force normal. Pulling it upwards, and it's an elevator, it weighs a lot, it's in air, so the thing pulling it down is the force gravity. This is generally going to be the case. So let's say that there is an elevator that weighs 1,000 kilograms. So 1,000 kilograms, and I want to, this is a similar question, it's moving downwards at a constant velocity. And this is all they'll give you. They'll say, what's the tension, basically? This is a simple version of the question. 1,000 kilograms moving down at constant velocity. Well, what's the force gravity going to be? Just 1,000 times 9.8. So we're going to say 9,800 newtons going straight down. And, okay, well, we don't know the tension, that's what they're asking for. So we can think about the sum of the forces. We said it's moving downwards, right? So let's go ahead and just say that direction is positive. You could say that up direction is positive, you get the same right answer, but because it's moving down, it makes it easier if we just assume that that is positive. So 9,800 is one force vector. The other force vector is the tension, minus, because we said down is positive, which means up is negative, so plus and negative, minus. This is equal to the mass, 1,000, and it's moving down at constant velocity, so the acceleration? 0. So this is kind of the same example that I just did with the force friction. We're going to say that 9,800 is equal to the tension. And you set it up just like that. It doesn't have to be any more convoluted. It's honestly, this formula simplifies the crap out of everything. In another way they could ask like the exact same question, and it just makes it seem harder, is they'll say, okay, an elevator weighs 1,000 kilograms and it's moving downwards at a constant velocity. Now the tension, the maximum tension that this cable can hold is equal to 10,000 newtons. Does the cable break? We don't have to do any more work, we still solved it. They're saying the maximum tension is 10,000, our tension is 9,800, this is smaller than this, it's not going to break. How would the question change if it was moving upwards? Intuitively, you might think something's got to change, but it's still going to be 9,800 minus t, or you could say, if you want to say the direction of movement is positive, t minus 9,800. If it's moving down at a constant velocity, moving up at a constant velocity, we nevertheless have an acceleration of 0. So in any of those cases, the tension is going to be 9,800. Whether it's moving down at a constant velocity, moving up at a constant velocity, or if it's just sitting there. Any case, it's all the same. And that again is so weird, but constant velocity is constant velocity. It means the sum of the forces is equal to 0. So, same question, we're going to change one little thing about it now. They could say that the maximum tension is 10,000. And they'll want to know if this thing weighs 500 kilograms. What's the maximum acceleration upwards? So a free body diagram, never going to really look any different. We just have to think about it. Well, force gravity, again, is the most reliable force. It's just the mass times the gravity. 500 times 9.8 is 4,900.
Are we keeping that max tension? Is it 10,000?
Yes, max tension, tension max is staying the same for this problem. So the maximum acceleration upwards, how hard is the cord going to be pulling it upwards then? It's all 10,000, right? If we wanted to accelerate as much as possible, this should pull stronger. If I want to accelerate, if I pull this up a little bit, it might accelerate a little bit. If I pull it harder, it's going to accelerate more. So if we want the maximum acceleration upwards, we need to make it the full 10,000. How am I going to set this up to find the acceleration? Well, which direction is it moving?
It's moving up.
So we're saying that's the positive force. So I can say 10,000, okay, well minus this one because it's going the other direction, minus 4,900 is equal to the mass, which is just 500, times the acceleration. 10,000 minus 4,900 divided by 500. The acceleration is 10.2. We said up was what direction?
Positive.
Yeah, up. And so this is a positive number, which is just saying what we wanted to say. The acceleration is 10.2 up. That's the maximum possible acceleration. What is the maximum acceleration downwards? Well, what's the maximum acceleration for anything downwards on Earth? Just gravity. If this tension can only pull something, then we're basically going to say, okay, the maximum acceleration downwards is going to happen when this cord is like broken or it's not doing anything. And in that case, tension equals 0. And now we say that this is the downward direction. So 4,900 becomes the positive value in this case. 4,900. So we want to find the maximum acceleration downwards. So, well, it's moving down, so we know this is positive. And if it's the maximum acceleration we're looking for, we want the rope to be doing the least amount of work pulling it upwards. So 4,900 minus 0 equals the mass, 500, times the acceleration. Well, obviously the acceleration is going to be 9.8. So with a lot of these Newtonian mechanic things, they should make sense. Like you kind of have to get over a little hump of like unintuitive stuff, like things moving forever unless they're acted on by other forces, and like Newton's third law forces. But you would set it up just like this to get something that you should intuitively have guessed. What's the maximum acceleration for anything downwards would be 9.8, assuming we're not pushing it downwards, which is not how elevators work. Okay, so one more question, and then I guess I'll look to see if you guys have any questions. Or any questions now? No, okay. Let's say this is an unknown mass. And this is a mass of 10. And I'm pulling this upwards with 100 newtons. I want to know what the tension is here. What's the tension? Okay, so when I have two things in contact, first step, make it one big thing. So this, very quickly, just becomes this. 10 plus A. This is kind of like the problem I was trying to do earlier, but it's a little different because this one's moving in the Y direction, the other was moving in the X direction. So let's say that this thing, even though it's being pulled up, it's moving down at a constant velocity. So my arm is pulling this up. I can still lower it. My arm's not lowering it, gravity is lowering it. My arm's just not beating gravity. So this is me pulling up while it moves down at a constant velocity. So that is possible. So we're pulling it up with 100. It's moving down at a constant velocity. Just in the same way that I want you guys to just have like a visceral reaction when you see something at an angle. Anything at an angle needs to be broken into X and Y. Anytime you hear constant velocity, you have to think the sum of the forces equals 0, the acceleration is 0. So we're going to assume that the acceleration is 0, and we'll come to that in a minute. What's pulling this down? Just gravity. Gravity is never going to change. In the same way that in chapter 2 and 3, we're saying no matter how hard you throw it up, it's always 9.8 meters per second squared going down. So this is just going to be force gravity.
It's 10 plus m, right?
Yes, so now it's 10 plus A. That is the mass.
Why is the mass 10 plus a?
Or 10 plus m, sorry. You're right. 10 plus m, just whatever we want to call that. I thought I called it block A, but I called it m. So 10 plus m is our overall mass when we combine the two. 10 plus m times 9.8. Okay. And ultimately I want to know the tension of the string. So I'm going to set it up like this. The sum of the forces. We said it's moving what direction? It's moving down at a constant velocity. So I'm just going to go ahead and say this is the positive. I don't have to, but I just would make my life maybe easier. So let's say it's 10 plus m times 9.8. So this is all one force minus the opposing force. So this is down is positive, means up is negative. So minus 100 is equal to the mass 10 plus m times the acceleration. Well, it's moving down at a constant velocity, which just means the acceleration is 0. In which case, that's 0, and I get 98 plus 9.8 m is equal to, if I add this to the other side, 100. And let's see, 100 minus 98 divided by 9.8, 0.2. It's a very small mass. Mass is equal to 0.2 kilograms. Great. That wasn't the final answer though. They want to know about the tension. So just the same way we did earlier, your first step when you got like something in a system is you say, okay, it's just one huge thing, some of the masses. You solve for whatever you can. Sometimes it's the acceleration. This was a weirder question. The only thing we could solve for was the mass. Well, now I have the mass, so I can plug that in here. 0.2 kilograms. And I want to now inspect this individually. I'm going to look at the free body diagram just for this individually now that I figured out the mass by being smart and combining them. So just this 0.2 kilogram box. the force is directly applied on it. The 100 newtons is going directly up. It's touching it. There are two forces pulling this down. There's a force of gravity of this block itself, which is equal to 0.2 times 9.8. There's also going to be a force tension. There's a rope pulling it. The tension is basically brought about by the 10 kilogram thing pulling the top block down. So that the tension in the rope is pulling it down as well. And that's what we don't know. That's what we want to find out. So I have all my forces for this one particular block. And I know it's moving downwards, so let's just say that these directions are going to be the positive. So I can say 0.2 times 9.8, which is 1.96, plus t, plus because they're both going down and we're just saying down is positive, minus 100, minus because that's going the opposite direction of what we said for this particular problem was positive, is equal to 0.2. If it's constant, that just means 0. This whole problem would have been the exact same if it was accelerating down at 3 meters per second squared. I just would have said, instead of 0, I would have said 3. That would have given me a different number. And again, instead of saying 0, I would have said 3. My entire approach would have been the same. If it was 3 meters per second squared up, I still would have said 3, but now I would have made this positive and this the negative. And the approach is the same, regardless of how you spin it. I'm just really hammering in that constant velocity thing, because they do that a lot. Okay, so this is 1.96 minus 100, and is a tension of 98.04. Tension is equal to 98.04. That's the tension pulling the 0.2 kilogram box downward. That was the answer, that was all I wanted, but just to really see how Newton's third law and a lot of these tension problems work, the tension pulls the top block down. So we're pulling the top block up, the gravity of the top block pulls it down, as well as the tension pulls the top block down. That same tension pulls the bottom block up, because the question is what's pulling, I've got, a rope and it's attached to one, and then the rope's attached to another. So my 100 Newton force is not touching this. It's pulling this, and this is pulling the rope, and the tension is what's pulling this up. And we should expect these tensions, the tension pulling this down should be equal to the tension pulling this up. So if I look at the free body diagram for just the 10 kilogram box, it's a tension, which we're going to assume is the same as this one, 98.04. And the force gravity here is 98. So the sum of these forces, if it's going down, should be 98 minus, we'll approximate this 98.4, is scary close to just 98, which is equal to the mass 10 times the acceleration. And again, we get 0 is equal to the acceleration, which is what we want. So take away the tension pulling down will be the same as the tension pulling up. That would have been the same for the previous problem, which I kind of goofed up by giving you friction, is if I pull this, there's a tension pulling this to the left, and that's the same as the tension pulling that to the right. That's how tensions work. Cool beans. Sorry, I guess I'm erasing. You guys good with that? Okay. So what am I not touching on that he touched on that you guys want me to go over? Now we have another 10 minutes or so.
Do you think it's important to go over apparent weight in the elevator?
Yeah, let's do that. That's a good one. I actually thought about that, and I didn't know if we have time, but we were done early with all the ones I thought about. So yeah, that's great. So apparent weight is very similar to the elevator problems we were doing, just with one other little twist in there. So previously we did an elevator problem, and we were looking at the cable at the top, but now we're not looking at the cable. We're just looking at what's happening inside of the elevator. So it's just a free body diagram of a slightly different thing. Instead of the top of the elevator with the rope, we're just looking at what's going on inside the elevator. So the idea is there's a scale, and you're standing on the scale, and let's say you're me and you weigh about 100 kilograms. So how do scales work, basically? Scales measure forces, and then they just divide that number by 9.8. That's how scales work. So this is a stationary elevator, stationary. So my force gravity is equal to 980. So what's my force normal if it's a stationary thing? 980, going up. Who supplies the force normal? We normally say the ground, right? But I'm technically not standing on the ground, I'm standing on the scale on the elevator. So the scale, this beautiful thing here, is pushing up with 980. The scale is smart, and it says, okay, 980 is how much we're pushing in, divided by 9.8. This is what it will read to you. It will read to you 100 kilograms, because that's how much I weigh. So it just realizes the amount of force that it needs to provide, and it divides that by 9.8, and that gives you the mass of the thing. So we're going to do the same question, but it's no longer stationary. The acceleration is 2 meters per second squared down. First of all, I really want you guys to get good at like having gut intuitions, predictions. What happens when the elevator goes down really fast? Like if you guys have been in Tower of Terror or Dr. Doom's ride or Disney's where elevator goes down fast, do you feel heavy or weightless? Weightless. So I would expect that to be reflected in the answer. The mass that the scale reads should be less than 100. That's what our prediction says. So let's do that. Now, forced gravity is reliable. It will never, ever, 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 ever change. Force normal, we said that was very fickle, so it will change. So this 980 cannot be trusted anymore. I don't know what the force normal is. So I know the force gravity, and I know the acceleration, and I don't know this. But I know that this is all my free body diagram, right? I don't have to worry about the other forces because I'm only talking about specifically my mass, not the mass of the elevator. And that's the slight difference between this problem and this problem. This problem was worrying about the elevator. We're not anymore. We're just looking at the person. So the elevator is kind of irrelevant. You could have just been like on like a springy thing that's pushing you up or pushing you down. So the sum of the forces, we're moving down. So which force should we say is positive? Yeah, it just makes our life easier to say, okay, 980 is the positive force. That makes force normal the negative force, so minus the force normal. Okay, that's equal to the mass, our mass, which is 100. Our mass doesn't change, right? We're talking about apparent weight is sort of the idea of the problem. Our actual mass is 100 kilograms. The Earth is not going to be tricked. It says we know we're 100. So 100 kilograms times the acceleration. The acceleration is not 9.8. Remember, the elevator is going down at a nice acceleration of 2 meters per second squared. So that's our overall acceleration. I only have one variable, the force normal. Again, this is it. All these problems might look kind of different. The more I knew this, it almost makes me less valuable because I forget like what it's like. But all of this is the exact same. It's just the sum of the force equals ma, like every single problem basically. Okay, so 980, force normal, 200. That's 780 is equal to the force normal. And the elevator, or sorry, not the elevator, the elevator, and then I said escalator, the scale is basically just going to take this number, 780, and divide it by 9.8. That's how it operates. 780 is the force normal provided by the scale. Well, 780, the force provided by the scale, divided by 9.8, gives us 79.6 kilograms, which is exactly what we thought. We thought we would be lighter in terms of what the scale reads, and we are lighter in terms of what the scale reads. Our mass is absolutely still 100, but the scale reads 79.6. We feel lighter as well. Though a lot of that has to do with our biological system and like stomach. But okay, so let's do the same thing, because these are good problems. They do like to ask, especially the MCAT. Adler's been actually really finicky. He completely changed the mastering physics questions from the last 2 years, which has got me a little worried. And he didn't give you all a practice exam, right? It was like learning catalytic stuff. Yeah, so, I mean, the principles are obviously the same. Newtonian mechanics is Newtonian mechanics, but he is asking weirder questions. So traditionally he asks a lot of elevator problems, but I always hate trying to predict what Adler is going to ask just because he is very dynamic, let's say. So same thing, let's say it's accelerating up 3 meters per second squared. Okay, I want to just, for the sake of making life easier, say the upward force is the positive one. So this is force normal minus 980. Again, we don't know what force normal is because it's very variable, it changes. But force gravity is old faithful. It's always going to be whatever your mass is times gravity. So 490 minus 980. And also for force gravity, we're ignoring things like, yes, technically as you go higher above the Earth's atmosphere, your gravity gets less of an effect on you. But that's so negligible that we don't worry about it. So force normal going up, direction of movement, minus 980 going down, is equal to our mass, 100 times the acceleration, which has been provided, 3. And in this case, it's 300 plus 980 is 1280. Force normal is equal to 1280. 1280 divided by 9.8 is 130. And again, this is something we could have predicted. When the elevator goes up really quickly, you feel like compressed, you feel heavy, and that's what this scale is measuring. So the scale is basically saying, all right, 1280 is how much I have to push up on this fatso, divided by 9.8, which is equal to the apparent mass, 1280 divided by 9.8, which is 130.6. 0.6 kilograms. And I mean, they really could have just, the only other way they could ask this problem is they gave you the force gravity and then they gave you the weight that the scale has, and you have to calculate the force normal, and then you would have to go ahead and figure out what the acceleration was. So let's do one of those really quickly. But it's almost the exact same thing. Okay, so
the apparent weight is the one that the scale is saying?
yes,
Okay.
that's what they, yeah, absolutely. So okay, last question, same idea. And actually there is one more I want to do. So we'll do this one more and then we'll take a break and then start the review. So if, let's say they say that the scale reads apparent weight or apparent mass is equal to 120 kilograms. What's the acceleration? That's the same exact question, they just gave you different variables. Okay, well, apparent mass is 120 kilograms. And we know that the scale basically takes whatever the force it has to provide and divides 9.8. So the force of the scale, which is the force normal, divided by 9.8, it's just an intrinsic mathematical property that the scale does, is equal to 120. So 120 times 9.8, which is 1176, is equal to, sorry, not the mass, the force normal. What's our sum of the forces look like for this? What minus what equals what?
1176 minus 980.
Yeah, why do we start with 1176?
Bigger.
It's bigger. That's as simple as we need to take it. The bigger number is probably the direction we're going. Makes life easier to say that's positive. So 1176 minus 980 is equal to the mass, still just us, 100 kilograms, times our acceleration. We don't know that, that's what the question wants. That's our only variable, 1176 minus 980 divided by 100. The acceleration is 1.96 meters per second squared up. What's funny is I feel like, because I've never actually really done it with the camera before, so I feel like I'm probably blocking it too much with my body. I did like a 2-minute test run yesterday, and I was like, I need to make a note to not block it so much, but I feel like I am. So people, if they're watching this, are going to do exactly, who's taking bio, you just took biochem, right?
The annoying guy.
The annoying guy, yeah.
Yeah,
I feel
he-
bad because he went to NYU, so someone can know him. He's very helpful, but his voice is a tad
So
annoying. But he always stands in front of it, and I'll like flash. I don't know. Have you looked at AK lectures?
No.
He went to NYU, but he has a bunch of biochem videos. But he'll always stand in front of it, and I wait till he goes off screen, and I'll pause it because he has everything written up, and then I'll just read it. So I just imagine people like, get out of the way, Will, get out of the way, and then just pausing it the second I do get out of the way. All right, so the last one that I wanted to show you, this was on, I forget if it was the exam last year or the practice exam he gave last year, but it's a really minor note, but it's annoying, but I want you to know it because it could be asked. This thing weighs 10 kilograms, and I'm trying to remember exactly how he phrased it. I don't remember the exact phrasing, so I'll have to give you the gist. So we're pulling at an angle. So this is, I'm really hitting at 2 points here. So actually I'll hit both points one by one. Let's say the force is 100 newtons. I want to know the acceleration of this box. So this is part one of a two-part question. Okay, blah, blah, blah. Well, maybe not so blah, blah, blah. But the force of gravity is 98. It's going down. How do I know that? Because it's always the mass times the gravity. 98 going straight down. I guess, yeah, so not blah, blah, blah. Normally we go, okay, obviously then the force normal is 98, but not so fast. Before we do anything, we hate angles. Let's break up the angle before we do a force body. So this is a 30-degree angle, which means we're pulling it at 100 newtons. I get a weird angle. We hate angles, so we're going to break this up into force X going to the right and force Y going up. This is 100 cosine 30, which will be equal to 86.6. You'll have your calculator, you'll do that. This is equal to 100 sine 30. Sine 30 equals Fy over 100. 100 sine 30 equals Fy. Which we should also remember, opposite of 30 is always half the hypotenuse, so it's just 50. 50 newtons going up. So screw that 100, I don't want it anymore. So I'm going to assume that everybody makes the mistake. And everyone said, okay, force gravity is 98, and force normal is 98. But remember that you could always do the force Y check, right? A lot of the times you'll do, okay, 98 minus 98 is equal to 0. That's the acceleration in the Y direction. But that's not the case here. We've screwed up. So let's look at our Y, sum of the forces. Let's say that this is, now let's say this one's positive. So it's 98 going up minus 98 going down is equal to, well, wait a second. We've got another force. We've got a force Y with 50 going up, so we're not done. We also have to say plus 50 equals 10 times A. But that means that I have some acceleration. That's 5 is equal to the acceleration. And it just seems unlikely. Actually, I don't want to take that because I'll mess up the camera. But this is my mass, this chair here. If I pull it, not too hard, but a little bit, it doesn't come up off the ground, does it? If I pull really hard, it will. But the idea is, as I start pulling, I'm pulling up, but the chair is still on the ground. All I'm doing is making force normal smaller. So basically, force normal is like, oh, geez, man, thanks for helping out. I don't have to work so hard now. I'm thinking of like Atlas in Hercules, where he offers to hold the sky for him. But I don't have enough time to explain the metaphor, so we're going to forget about my Atlas Hercules metaphor. The idea is, because we have 50 up, this doesn't have to be 98, because we don't have an acceleration. They kind of have to tell you. They have to say, you're pulling so hard it comes up off the ground. But if they don't say that, you're going to assume it's not. Basically, if we pull up with 50, this is going to go up with 48. What if I pulled up with 97 newtons as my Fy? What's my force normal? 97 plus 1 is 98. It's just going to be 1 newton up. And then if I pull with 99 newtons as my Fy, okay, at that point now there's more force up than force down, and we'll start to accelerate upwards into the sky, which could happen. But if they basically, force normal will get smaller and smaller and smaller and smaller and smaller until it's 0. So yeah, that's important here. The force normal is 48. And okay, so that was a side note. We're still in part one of the question. So the force normal is 48 up, Fy is 50. So in this, it's 98 going down minus 48, because of the force normal going up, minus 50. And this is all because we said down is positive. So, sorry, yeah, down is positive means this is minus and the 50 is minus equals 10a. 0 is equal to the acceleration. Cool, we are not interested in the y direction. We want to know about the x direction. There's no friction, so we only have one force, 86.6 to the right, 86.6, that is the sum of all the forces, it's the only force, is equal to 10 times the acceleration. 86.6 divided by 10 is 8.66. When I pull this block with a 100 Newton force oriented at a 30 degree above the angle, it will accelerate only to the right at 8.66 meters per second squared. That's that problem. That's how you do that. So I guess if you really fudged up and you said the force normal was 98, you wouldn't have really realized your mistake. But with part two of the question, you will have realized your mistake. So again, I forget exactly how he phrased it, but it was along the lines of this. I have a block. I think I have his language right. So actually I don't know this. So let's say it's a 10 kilogram again, which that means force gravity is 98. Okay, let's assume I don't pull on it at all. So this force is 0. Let's say it's 0, right? If this force is 0, the x component is 0 and the y component is 0, and the force normal is just 98 to counteract the force gravity. In the same way that I'm just standing here, my force gravity is 980 going down, my force normal is 980 going up, I'm not going anywhere. Same thing, 98 down, 98 up, because I'm not pulling it. But as I start to pull it kind of upwards, the force normal gets smaller and smaller and smaller and smaller, because it's kind of working in tandem with my Fy to counteract the Fg. So the wording of the question was something along the lines as follows. You pull this 10 kilogram block at an angle to the point where it just starts to leave the ground. What is the acceleration? He might have said to the right, I don't know. Let's give him the benefit of the doubt. What is the acceleration to the right? As soon as this block just starts to leave the ground. Well, the block just starts to leave the ground when the acceleration is 0. Or you might say when it's 0.00001 meters per second squared up. So what we're kind of going to do is assume, okay, what he is saying then is we're pulling now with some force. We don't know what it is, but we know that its y component is 98, because that means this is 0. And that means if it's 98 or 98.00001, it's just barely going to start going up off the ground. And he will say that it's 30 degrees, and he basically just wants to know what's our Fz, our hypotenuse. Fz is 98, Fy is 98. And I have the 30 degrees, blah, 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 SOHCAHTOA, trigonometry, you can figure that out, Fz, but it's gonna be twice as much because it's opposite of 30. So it's gonna be 196 newtons. That would have been your answer. You have to pull with 196 newtons for the y component to be 98. When the y component's 98, it counteracts the the Fg going down with 98, which means your force normal is not doing anything. And that's like just kind of sort of where it starts to levitate off the ground. Imagine that 98 is very similar to 98.1, which is where it just starts to accelerate. Actually, no, sorry, that's not the answer. They asked for the acceleration, which means I can solve for my Fx. So maybe they ask for Fz, maybe they ask for the acceleration. We'll do both. Fx in this case is going to be 98 root 3, or you'll do some other trigonometric function. 169.7. Okay, well that's my only force going to the left right. So if I want the acceleration to the right, it is just this one force. The sum of the forces in the x direction is equal to 10 times a. So my acceleration is 16.97 meters per second squared. And there we go. Okay. So that's Newtonian mechanics. Let's take like a couple minute break and then like no more than 5 minutes and then do the review. Or actually, anyone have questions on this first?
Why is it only in the x direction though?
Because if we still, I mean, that's a good point. If we still look in the y direction, again, if you're ever unsure, always just do the sum of the forces. This is like the super amazing formula that does everything, but you have to separate it for the y and the x. So some of the forces in the y direction here is 98 plus 0 minus 98 equals 10a. Except a sub y is equal to 0. There is no acceleration in this
So there's
direction.
not enough force to lift it.
Because there's not enough force. You know what you could have done? You could have said that, okay, this is 98.1, and that's where it just starts to accelerate, because then my acceleration is 0.001 or something. That's just started to accelerate, which gives me pretty much the same answer. You know, it's multiple choice, it's A, B, C, D.
Right.
Just starting to accelerate, you could say the acceleration is 0.1, or it's 0.0001, or it's 0. They're all going to give you the same answer.
Okay.
But yeah, so always do the y and x if you're ever unsure. But in a lot of cases, if you can just tell that the y components will cancel, which maybe it wasn't so clear in this one, if you can tell, you can just forget about it and just look at the x, because that seems to be the important thing. Otherwise, go ahead and say, okay, we have our y, sum of the forces equals ma, and then we have our x, sum of the forces equals ma. Well, there's only one in the x direction, and that's 169.7 equals 10a. Therefore, a is 16.97, and that's the answer. Yeah, cool.